We now move to the 2015 Thomas Rankin Lyell Award. The Thomas Rankin Lyell Medal recognises outstanding achievement by a scientist in Australia for research in physics and mathematics and is awarded every 2 years. The recipient of the Thomas Rankin Lyell Award in 2015 is Academy Fellow Professor Michelle Simmons, and I invite Michelle to come.
Professor Simmons has pioneered a radical new technology for creating atomic-scale devices, producing the first ever electronic devices in silicon, where individual atoms are placed with atomic precision and shown to dictate device behavior. Her groundbreaking achievements have opened a new frontier of research in computing and electronics globally. They have provided a platform for redesigning conventional transistors at the atomic scale and for developing a silicon-based quantum computer, a powerful new form of computing with the potential to transform information processing. Professor Simmons, congratulations. I would like to invite you to present your talk.
Thank you. Thank you very much, Jagadish, and I thank the Academy for this award. It's a hugely exciting time in the field of computer hardware at the moment. So we're going to start with this graph of Moore's law. So the last 50 years have been dictated by this law, Moore's law, Gordon Moore on the right-hand side, who's noticed that the number of transistors on a silicon chip doubles every 18 months to 2 years. For that law to hold, it basically means the smallest feature size has to decrease at the same rate. And this little picture on the bottom left here is a transistor that's used in a silicon chip at the moment. It's typically around about 10 nanometers, the smallest feature size in that, about 5,000 times smaller than the width of a human hair. And there are 4 billion of those on a silicon chip that all have to work for this computer to run this presentation that I'm showing now. Now, the interesting thing is you can plot as a function of time how small the smallest feature will be. And you can see if you look at the top right-hand side, in 2020, we're going to reach the level of a single atom. So it's very difficult to imagine that you can make the smallest component smaller than a single atom. What we decided here in Australia was using technology of a scanning probe microscope was to try and engineer devices at the atomic scale now. So we started this program in 2000. We started making single atom devices. And the reason we're doing this is if you can translate from the left to the right-hand side of this graph, you can see we go from the classical world to the quantum world. And in the quantum world, it's predicted if we can use the power of quantum physics, we can actually make computers that are exponentially faster than classical computing today. But it really requires we have to engineer matter at the atomic scale. So how does a classical computer work? Why is it so powerful? It does things one after the other very, very quickly. So if I was to write down a telephone number on a piece of paper and I didn't know whose number it was, I would get my classical computer to search the directory. It would start at the A's and go through the B's and the C's, and eventually it would find the number. It has to do it one after the other. If I wanted to go faster, I'd put 2 classical computers and I'd split the directory. If I want to go faster still, I'd put 3 classical computers. And that's kind of the underlying theme behind multi-core computing at the moment. Still, it has to do one thing after another. And that's what limits that kind of computational power. If I go to the quantum world, I can actually start to do things in parallel. So I can look at the whole directory at one time. So to try and give you a picture of what that means, at the moment, we're highly limited by what we use. We use 2 states of matter. We use ones and zeros. A transistor is either on or off, and that is how we encode information. So you can imagine we're either sitting facing the North Pole or the South Pole, and those are the only 2 states we use. In the quantum world, however, we can point to anywhere on the surface of the Earth. And as a consequence, what that means is we're in a combination of the down state and the up state at the same time. So if we go to the smallest component of a quantum computer, a quantum bit, it's akin to a classical bit, but it's now what we call a qubit. And there it can be in both the 0 state and the 1 state at the same time. And we basically now need these 2 parameters, alpha 1 and alpha 2, to describe that state. If I now go to a 2-qubit system in the quantum world, I now can have the 2 spins. In our system, we're using spins either up, up, down, 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 up, or down, up, down. And I now need these 4 bits of information, alpha 1 to alpha 4, to describe those 2-qubit states. And so what happens in the quantum world is every time I add a quantum bit, I'm essentially doubling the computational power. And that is the power behind quantum computing. So by the time I get to 30 qubits, it's more powerful than the world's most powerful supercomputer. If I can get to 300 qubits, it's more powerful than all the computers in the world connected together. So there is a huge international race to try and build one of these computers. And to give you an idea of a kind of problem that you can solve with this, we typically call this problem the traveling salesman problem. So you have a salesman who wants to go to lots of different cities and find out what the shortest possible route is. is what we know as an exponentially hard problem. So the number of possible routes grows exponentially as you increase the number of cities. So if I take a classical computer and I ask, what's the shortest possible route if I'm going to 14 different cities? There are already 10 to the power of 11 routes, and with a classical computer, it would take about 100 seconds. If I now ask that same computer, what's the shortest possible route for 22 cities? There are now 10 to the power of 19 possible routes, and it would take that same classical computer 1,600 years. And by the time I get to 28 cities, it's longer than the lifetime of the universe. So there are lots of what we call exponentially hard problems out there that we just can't solve. And the world of quantum computing is just beginning, really. The hardware is just getting to the point where you can actually make devices. But you can already start to see now that there are reports coming about how it's going to transform the computational industry. There are 4 main areas that you can look at where quantum computing will impact. And just to give you a flavor of some of these, obviously I've talked about distribution systems before. So people are starting to fund research in quantum computing to look at how you can get products around the world in the shortest possible way, in the most cost-effective way. You've got people like Google that are using it for search engine optimization, and NASA's starting to look at research now, looking at all the data that's coming from telescopes and how to look through and sort through that data. Google's also funding it for the Google car, so looking around at object recognition so they can see where there's an object or a person on the road. So lots of information coming in. Companies like Lockheed Martin are starting to look at it in the aerospace industry. So when you have a jet fighter going along, it's got lots of information coming. If they want to determine what is the missile, there's a huge amount of data they have to process real time. And if you can do that in parallel, it would obviously make a big difference. Drug design is another industry that's starting to get interested in quantum computing, because obviously it takes a lot of money to take a drug through the trial process. And if you can get the computational power up, that will go much faster. And I guess one of the first applications was decoding, so encryption and decryption of information. That remains one of the long-term goals of the field. Well, so how would you build a quantum computer? We had a fellow, Bruce Kane, who came to Australia back in 1998, and he said if you could build a quantum computer in silicon, that would be the ideal material to do it in. If you can build it in silicon, then basically you have a nice host material to host that quantum computer. And if you could engineer these single atoms, and you can see them in the slide here, these are the phosphorus atoms, you can actually encode information on those individual atoms, in particular in the spin states of those atoms. So you put it in a magnetic field, it either aligns with the field, like a little bar magnet, or against the field, and that's your two different states. But you can actually rotate it on what we call a Bloch sphere, anywhere in between. So that's the advantage of using silicon. The disadvantage really is you had to engineer the whole device at the atomic scale, and that's really what we've developed in our labs over the last decade and a half. So here is the kind of device we're heading for. We call it the quantum integrated circuit. What we're trying to do is to put individual atoms into that surface, and here's the kind of first result we got for putting a single atom deterministically into a device. And I have a little movie here of how that works. So we use a scanning probe microscope. I'm going to show you a silicon chip that we're going to zoom into. So there's the chip with markers on it, so we can find where we're going to put the atom down. We zoom in, you see the individual silicon atoms on the surface. We now come down with a layer of hydrogen that acts as a mask material. We then bring a very fine metal tip in, and we strip off exactly 6 hydrogen atoms from the surface. We now want to bring our phosphorus atom in as our qubit, so we use phosphine gas, and we get it to controllably interact at the surface. We force 3 pH3 molecules to dissociate to pH2 in the center. We then controllably heat this up. So we take a pH2, we'll grab a hydrogen and come off the surface when you heat it. Allows another pH2 to dissociate to pH. Another pH2 will grab a hydrogen, and now we can get that phosphorus atom to actually go through the crystal, heat it up a little bit more, into the silicon, and it kicks the silicon out. So you can actually see that whole process in these scanning tunneling microscopes. We then get rid of the hydrogen, and we encapsulate with silicon to provide a robust device. That's how we get the atom in there. There's the silicon coming down. That makes it a really robust qubit that doesn't interact with the environment. But we want to address it. So at the same point that we put that single atom down in the middle, we also pattern leads using the same technology. And these leads go all the way down to just a few atoms wide, so we can address that atom electronically. We then zoom out, using those markers, put down contacts to the final device. So that's how we make these devices. And what I just want to show you in the next couple of minutes is how we've systematically gone through and demonstrated all the different components of this quantum integrated circuit. So we've put down our single atom. We've made these very fine wires. Quite surprising, we found the wires have the same current carrying capability as copper, so very low resistivity, so we can make them very, very thin and bring them right in to address our individual qubit states. We then have to be able to initialize the spins on this system. So we're using spins. We have to be able to say whether they're going to load a spin up or a spin down, and then we have to read them out. And the way we do this is use these kind of devices called single electron transistors. And the whole point of this graph is to show you each little blip here in the conductance of this device is measuring 1 electron hopping on and off the central island on the right-hand side. So we have the control. We can actually get 1 electron to come on and off. but we also want to be able to initialize the spin state. So we take one of these single electron transistors, this device here, and we put it next to one of the atoms so that we can actually load and unload the spins onto the system. And this little graph on the right-hand side here is showing how if you want to load a spin-up system, you can get this little peak in the current that tells you you've got spin up, and if you want to load a spin down, you don't get a peak in the current through this single electron transistor. So in such a way, we're actually able to load and unload these single spins inside the silicon system. Very recently, we published our first two gate results. So we now have 2 spins. We're transferring a spin from one atom to another in this crystal, about 10 nanometers apart. And we're actually able to measure the wave function. This is another unique thing that's coming out in our labs now, working with a new professor at UNSW, Sven Rogg, so we can actually see the individual wave functions of the atoms we're trying to engineer. And systematically now what we're working towards are 3-qubit devices, 4-qubit devices, and by the time 2018 to 20, we're going to get the 10-qubit device. That's our kind of roadmap. Well, there are 7 different things you have to realize to build a quantum computer. I won't have time to go through them all, but essentially you have to be able to get a well-defined quantum system. You have to initialize the spin states. You have to control that the coherent operation of those spins is longer than any operations you want to do with a gate. You have to be able to measure the spin out, and then you have to form these gate operations so you can actually write information into the computer, do a calculation, and read it out. That's currently where we're sitting. It's a very competitive field internationally. Australia is actually at the lead of this in the silicon field. What we're trying to do in the next few years is to realize the last 2 of those, what we call DiVincenzo 6 and 7, to build the first kind of quantum system. And just in the last slide, I've gone over my time a little bit, but how long is it going to take to build a practical system? We can go back to the classical industry. We can see from the invention of the first transistor, it took about 10 years to get an integrated circuit, and then it took another 5 years to get first kind of commercial products. And we've tracked that now for 2 different transistor types. So what does that mean for the field of quantum computation? We think it's another 5 years or so before we get the first integrated circuit by the time 2020. And then after that, it's about another 5 years before we'll start to see some really exciting hardware come out to do quantum computation. So thank you.
Thank you, Michelle. Are there any questions or comments to Professor Simmons? Let me start off with the question about the scalability issues. What do you see as the major challenges in terms of scaling them to, say, for example, 30 or 40 qubits?
It's a very good question. So when you're working at the atomic scale, you're literally using individual atoms, but you have to address them with things that are bigger, that you can actually connect to the outside world. So that ability to get the contacts down to those small atomic scale devices is a big challenge. And so what we do is we look at different ways of designing the architecture and reducing the number of gate density in there. So if you can reduce the gates, you don't have so many to get down. And if you can actually go to 3 dimensions and pattern in 3 different dimensions, then you can actually get fewer gate densities overall. So the innovation in the field is really coming about from how do you get the contacts to those devices and make it a scalable system.
Thank you. Robin?
Michelle, you used a wonderful demotic phrase, we grab the atoms. How do you grab the atoms?
We actually don't grab the atoms. We literally manipulate the surfaces to create spaces where they want to go. So we create low energy positions where the atoms will naturally go, and we control the chemistry to make sure they stay there. So we use the scanning tunneling microscope, which is a very fine metal tip that images atoms. We actually use that as a tool to create these templates where those phosphorus atoms will go down in the lowest energy state to go there. And then what we try and do, which is what industry is also doing, is use low temperature processes throughout to keep the atoms where we want them. And I think one of the exciting things we found is we really have that control in all 3 dimensions to put an atom there, encapsulate it, be able to address it. It's very exciting.
Scott?
You mentioned the traveling salesman problem.
Yeah.
Do you think quantum computers offer an exponential speed up for traveling salesmen?
No, well, so there are what we call NP hard problems. So there are exponentially hard problems that quantum computers will be able to solve. That's an illustrative example, so it's not one that's been proven yet that will work. But yeah, it's an example of how something grows very, very quickly.
Well, on that note, could you please join me to thank Professor Simmons for a very stimulating talk?